Hello everyone, Dr. Chen here. So we're going to discuss kinetic energy and then discuss WorkEnergy Serum in this lecture video. Kinetic energy is defined in equation 1/2 mv squared. So it's the energy associated with the motion of particle. Now kinetic energy is a scalar quantity. It doesn't have any direction. 1/2 mv squared, so it's a number with a unit joules. It only depends on the particle's mass and speed, but not the direction of motion. And because m is always positive, v can be 0 or, of course, can be 0, positive, negative, but v squared always has to be positive. So kinetic energy is always positive. Kinetic energy is always 0 or positive. It cannot be negative. The SI unit of kinetic energy is joules, just like work. And then we can check if we put in the SI unit of mv squared is kilogram times meter square divided by second square. It's exactly the same as the SI unit of work. Now, those two objects with same mass m, same speed v, but different direction of velocity would have the same kinetic energy. If we have object m moving at a speed v, and then we have object 2m moving at a speed v, then the kinetic energy for this object would be double compared to the object with mass m, because kinetic energy proportional to the mass 1/2 mv squared, right? Now, on the other hand, if we double the speed, what's going to happen? How does the kinetic energy of those two objects compare? M are the same, and kinetic energy is 1/2 v squared, 1/2 mv squared, right? So this one actually have 4 times kinetic energy compared to this object, because kinetic energy in terms of speed is proportional to speed squared. If you double the speed, kinetic energy would be quadruple. If we have a system, we have a particle m1, we have a particle m2. If they're moving at velocity v1 and v2, then the kinetic energy of the system would be the sum of the kinetic energy of individual particles. Kinetic energy of this one be 1/2 m1 v1 squared. Kinetic energy of this one would be 1/2 m2 v2 squared. Of course, if they connected by a string, they should have the same velocity. Now, we are ready to learn what is WorkEnergy Serum. Now, we need to first go back to the concept of net force. Net force is the vector sum of all the forces acting on the object. And then we have net work. What is the work done by all the forces? It will be equal to the net force, the vector sum of all the forces times displacement. Now, suppose we have object m. The net force acting on it is F net. Then what's the acceleration? Acceleration is F over m, right? Okay. Now, it accelerated from an initial velocity v0 to a final velocity v. How much work is done by this net force? The work done is always should be F net times delta x. And from Newton's second law, we know the net force equals to ma. Net force equals ma. And we have a kinetic equation, the third kinetic equation. Final velocity squared equals initial velocity squared plus 2a delta x. So we can use from this equation, we can solve for this a times delta x because we have a times delta x here. A times delta x equals final velocity squared subtract the initial velocity squared divided by 2. And then we replace this a times delta x by the right hand side. We have the work done by the net force can be write as 1/2 mv squared subtract 1/2 mv0 squared. But this is exactly the kinetic energy of the object here. This is the kinetic energy of the object here. So we arrive at WorkEnergy Serum now. The work done by the net force equals to the change of kinetic energy of the system. So this is WorkEnergy Serum. This is our WorkEnergy Serum. The total work done on the object equals to the change of kinetic energy. Work done by the net force equals final kinetic energy, subtract the initial kinetic energy equals to the change of kinetic energy. So we can relate the work done by the net force to the change of kinetic energy of the system. Let's do one example. We have a space probe. We know its mass, we know its initial velocity, and we know a force acting on it. We know the displacement. I want to find out the final velocity. Now, of course, we know the force. We can calculate what's the acceleration and then use the kinematic equation to calculate what's the final speed. But after we learn the WorkEnergy Serum, it's not necessary anymore. We can just calculate what's the net force done on this object equals force times displacement, because in the angle between them, in our case, is 0. So we calculate the work done by this force. The force displacement, because in 0 give us 1. And we know the initial kinetic energy, 1/2 mv0 squared. V0 is 275 meters per second squared. We know the mass, so we can write down 1/2 mass times Vf squared is the final kinetic energy. So this is WorkEnergy Serum. Total work done by the force, final kinetic energy, initial kinetic energy. Everything is known except the final velocity, so we can solve for it. It gives us roughly 805 meters per second.